Continuing our discussion of redox in organic chemistry, we see that it's possible to put a couple new H's on an alkene using hydrogen. But if you don't have a catalyst, you don't get a reaction. That's what RXN means, no reaction. But with one of these catalysts, you get a thin addition. A thin addition. Yeah, I like this one. With thin stereoselectivity, because the two new bonds happen at the same time. And the mechanism, which is never tested, yes, write that down. Never tested. If you look on old practice exams, I've never asked it. I'm not going to start now. But for those of you who are curious, what happens is that the platinum, its job is to weaken this bond. So if I have a chunk of platinum with like thousands of platinum atoms, this is just a piece of platinum metal, everybody. Yeah. One of the reasons I don't ever test it like this is too much platinum going on. Some redox happens down here where this bond gets weakened. I'm going to exaggerate that so the bond gets broken. H delivers its electrons to that platinum, and this platinum gets electrons and delivers them back to the H. And I don't even have a pair of electrons down there. So it's not even a good mechanism, seriously. That's why I don't test it. And what you get is a surface of platinum. I'm going to short form the surface of platinum to this with two new H's on the sticking off of the surface, right? And then your alkene comes into town looking for some action. And I'm going to redraw that alkene, flatten it out a little. Oh, wow. I'm flattening it out just a little. There's the alkene, right? And this delivers to one side. Pi delivers there, and then the platinum gets reduced. So if I had two platinum atoms, the one on the left just got oxidized and the one on the right got reduced, right? So in terms of platinum, it's not really changing. In terms of hydrogen, hydrogen went from being bonded to a same electronegativity, HH, to a more electronegative carbon. So hydrogen got reduced. Sorry, more electronegative carbon, I misspoke, didn't I? If you're hydrogen, did you get reduced or oxidized? And what I just said was wrong. You're becoming bonded to a more electronegative carbon. The electrons moved away from you, your hydrogen. You got oxidized. But organic chemists don't talk that way. We only talk one way. We only talk about what happened to my organic molecule. That's when we describe redox, it's like we pretend only one of them's happening, whichever one's happening to my organic molecule. So this reaction is called a reduction. Why? Well, let's do oxidation states for the two carbons. Ox state, easy on the start one. Each carbon has 4 bonds to carbon. Oh, nobody got these sheets. Oh, you didn't get one of these sheets. Let's do it. Oh, yeah. Here we go. Sorry about that. Okay. Reduction. Ox states of carbon. When you have bonds to the same electronegativity, 0, 0, correct? What about 3 bonds to carbon, which is 0, 0, 0, and then a bond to a less electronegative hydrogen? What do you get? -1 and -1. Each carbon got reduced by 1. Each C got reduced by 1. Okay. Similar story down here, but opposite result, 0, 0. In parentheses, oxidation states are in parentheses on today in red. And when you're done, +1, correct? +1. It actually happened earlier than that. The oxidation happened after that first step, didn't it? Mm-hmm. Oxidation. And like I said when I was designing this document, and we kind of had half this lecture already, students are often guilty of, like everybody is, looking for shortcuts in life. And they see this and they think carboxylic acid. They do. They're wrong. That'd be an octet violation. The carbon on the left would have 3 bonds to methyl, 2 more bonds to a carbonyl, that's 5, and then a 6th bond to the OH of the carboxylic acid. So it's way wrong. I just want to point out that's tert-butyl with a peroxide. I hope you're not surprised. Its name is tert-butyl hydrogen peroxide. You know what it's called when it's an H on each side. You just call it hydrogen peroxide, right? I got my paint can. I don't know how. Wow. I just want my pen. Sometimes you just want your pen. Okay. Okay. It's an oxidizer, and it re-oxidizes the osmium back. And these are actually new O's that came from the tert-butyl hydrogen peroxide. So you can even be a stoichiometry guy and say, yeah, I need 2 moles of this. But I never grade stoichiometry unless I say I'm going to. The only time I ask for stoichiometry is when I ask for a balanced chemical reaction. So I got rid of the 2. Yeah, it breaks down the OsmiumVIII diester, the tert-butyl hydrogen peroxide, and it's an oxidation reaction. And what do you need to know? Let's summarize. You need to know for hydrogenation, you get 2 new H's on the same side. Can you predict those products? You need to know for the OsmiumVIII oxide in combination with tert-butyl hydrogen peroxide, did you get a vicinal diol? Vicinal is a new word for many of us. Vicinal means on adjacent atoms. So in this case, the word diol means there's 2 alcohols. Where are they? On adjacent carbons. Okay, and they are, aren't they? Vicinal diols are also known as, AKA, glycols. Glycols are vicinal diols. This is an appropriate time of year to bring up glycols because the weather's starting to get cold here in Michigan. Okay? You better make sure you got your glycol in your radiator. Why?
The antifreeze.
Yes. Anything added to water will lower its freezing point. Don't add salt to your water. It does a great job of lowering the freezing point, but it'll corrode your radiator. So, salt would be a great choice for the freezing point depression because 1 salt molecule gives two ions, which is like a molality of 2. But it corrodes your radiator. So you got to use neutral organic compounds like ethylene glycol.
First thing you wrote under this on your book, highly toxic.
Yeah, but it's very toxic, yeah. So you might want to use propylene glycol. You can buy it. It's the green antifreeze. That statement is incredibly misleading. It's green antifreeze because it's environmentally friendly, but they color the poisonous one green. Oh, my mind is blown. The green antifreeze, they often color it green as well, but they often give it a different color, like a blue. The colors are very misleading because green has two meanings nowadays, right? Well, green, the color is always green, the color. But
Are you talking about the blue water that doesn't freeze?
oh yeah, the blue water's got something dissolved in it with a blue dye as well. It's not the blue that's causing the benefit. They put a color in there. The antifreeze has no color, but you want to see that color so you know not to drink it, right? Yeah. Yeah. Okay, so that's oxidation. Yeah, there's another oxidation we're responsible for that takes it one step further. Let's just do it freehand here. Same alkene. And here's our old friend from a long time ago. I'll do its full Lewis structure so you can remind me its name. It's a zwitterion. What? Yeah, it's got two charges. It's O3. What's its name? Ozone. Now somebody said oxonium. I can't say they're wrong. It has an oxonium. That's the middle oxygen, right? But it's also got an oxide, right? That's the end oxygen with a minus. Ozone is it's a very cool molecule. And you're not responsible for any of these mechanisms, really, seriously. Never tested. Mechanism never tested. Never tested. And this one, mechanism required for this step only. Required for this step only. And here it is. It's a weird one. We've never had a mechanism attack an oxygen. Because oxygen's more electronegative, right? It's got a minus charge. But don't forget that thing in the middle, OS. What was its oxidation state? +8. Isn't that seriously asking for more electrons? Just by nature of its extreme charge? Yeah, that is like being a very electronegative element, isn't it? If you're a +8, say, anybody, I need electrons now. Give them to me. That's like saying, I'm very electronegative right now. I want your electron because I'm +8 and I don't like it. Okay, so it's pulling the electrons from the oxygen, and the oxygen saying, wait, this is a rare time in my existence. I'm actually starting to feel positive. Okay, the oxygen doesn't ever say that except now. And then the osmium gets a lone pair. You don't see that very often. Hey, 3 arrows at the same time. Do you understand why wedge now? If they're happening at the same time, they're the same drawing direction, okay? Either wedge or dash. You'll get 50-50, wedge, this picture, dash, not pictured, okay? And the breaking down of it, you're not responsible for the mechanism. You just need to know these chemicals will cause this to break down to these two things. So I want to break that down and make it very clear. What does he mean when he says we're responsible for the chemicals in here? Every time I say that, I mean one of three things. This could be a blank. And you are given this and this and this. Can you provide the blank? Similarly, this could be a blank, in which case you can give me either answer. And I would give you this and these two things. And similarly, this is given, one of these is given, and this is a blank. Okay? Same three possible questions for any reaction you're given ever. What are the reactants, given the other things? What are the reagents? Those are generally the inorganic reactants, reagents with a G. And what are the products? And I generally only care about the organic product. I'm an organic chemist. Now with ozone, what are you responsible for? You're not responsible for knowing anything green. Not responsible for green. But it is a kind of a cool story. The thing you get. Hey, even if you don't know the mechanism, you know those bonds happened at the same time, right? You don't have to know how they happened. Just looking at the picture, you know they had to happen at the same time. The wedge-wedge, right? Let's make sure they're very clearly wedge-wedge. And then it goes to another intermediate. So you guys are going to think the black's there. Am I responsible for that? Green-black combination, not responsible. Okay, and that breaks down to something without this bond in the middle. Whoa, it broke a carbon-carbon bond. And we got two of the O's out here. And one of them in here. Oh, that is just too cool, isn't it? Isn't that wild? You are responsible for this chemical. Responsible for this chemical. Here it is. CH3 bonded to S bonded to CH3. AKA S CH3 twice. Are we clear that's the same thing I did twice? Okay. And what happens is sulfur ends up like this. The carbons end up like this. Wow. If I could draw better, that should be two ketones. It should be two ketones. They just didn't draw it very nice. Sample test question. Based on just what you have on the screen. That's what you want to see, right? Sample test question in a pink box. And two is a box. You're right. A box within a box. Within a box. No, it's only a box within a box. Sorry. Random vocalizations during video. And it's only Monday. Wow. Okay. We're getting to that part of the semester. Things get a little crazy. So, I mean, we have the two answers on the page, right? First step, oh, the O3 is going to give you something like this, but you're not required to draw that. But once you treat that with the dimethyl sulfide, then you should be able to draw me this. I mean, if I ask for it, you should be able to draw me this too. You'll see some tests where I ask for that. You want that to be a box too? You want the whole experience. Then here's how I show that on the test. Contains sulfur. Now it's a more complete test question, the whole experience. And that's a clue what goes in box 2, isn't it? Better have sulfur. So let's copy paste this onto the next page. Got more than I bargained for, but that's okay. Let's erase the extras. Ooh, I erased some of my product. Oh, I did want to erase that. Never mind. That thing I just erased goes in the big box, right? So what chemical in box 2? S with 2 CH3s? Yeah. And the sulfur when you're done, S with 2 CH3s, but it took the third O, didn't it? It took the third O from ozone. You want to go back? Here's your 3 O's from ozone. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So here's the story on that. And this product, how do you predict this product based on the reactants here? That's what you should be doing. Let me show you. CH32F. Now, I'm going to show you the biggest visual on predicting ozonolysis products that you'll ever need. You agree you started there? You agree we started right there? Get your eraser. You ready? Done. Wow. That's the product. So tell me the steps. There's the reactant. Cut your double bond in half. Keep pi bond each way. 2 of the oxygens from ozone on the end of each one. Third one goes with your sulfur. End of story. Put this in the box where it belongs. And just drop it.
But this one does not split.
It did split.
I mean,
It didn't split to 2 molecules because it was attached in 2 different directions. Aha, yeah. Yeah, normally you'll get 2 products. It's called ozonolysis for a reason, right? Ozonolysis, because there was a cutting. Lysis, cutting. Learn this for many science classes, please. Okay? And yeah, we cut it in half, but the molecule still is 1 molecule because it was connected out here too. Lots of practice items on ozonolysis. I think that was good for today. Do we have any loose ends over here? Those were our last 3 reactions in chapter 6, everybody. And we're going to stop share.